A body having moving radially away from a planet of mass m, when at a distance r from the planet, explodes in such a way that two of its fragments move in mutually perpendicular circular orbits around the planet. So if I consider this as the planet, we have to find out various things. Let us say a body was at distance m, from the center is distance, let it be equal to r. They are going in the mutually perpendicular direction. Okay, they are going in mutually perpendicular direction. It means if I consider one fragment, it is moving in this direction, okay, in the circular orbit. And if I consider another fragment, it is performing a circle in 3D. Okay, in 3D this will look somewhat like this. Okay, it is performing circle in 3D, and they will again collide at this point. Okay, this is now now we cannot directly apply the law of conservation of the momentum, because I can clearly see that there will be other fragments also. Okay, only two of its fragments from its many fragments we are talking about. Okay, there will be at least, okay, in order to balance this, there will be at least 3 more fragments. Okay, but we don't have to go into the number of the fragments over here. Okay, we will proceed with this part. Okay, so we have to find out then their velocities in their circular orbits. Okay, if I consider their velocities in the circular orbits, the velocities are given as okay, in a circular orbit, if they are performing circle, the velocity of the first as well as the second, both of them are performing circular motion along the same radius r. So it will be equal to root gm divided by r. This is the critical velocity of a circular orbit. Okay, so the first question is answered. If I see the second one, maximum distance between the two fragments before collision. Okay, maximum distance between the two fragments will be when they are far away from each other, or when the first fragment is somewhere over here and the second fragment is somewhere over here. Okay, at half their distance. Okay, they are at the maximum distance. That is, if I represent it in 2D, this is the planet, this is the first and this is the second. So this is the maximum distance between them. So this distance is equal to r, this distance is over here equal to r. So the maximum distance between them will be equal to root 2r. Okay, it will be equal to root 2r, which is equal to option number B. Okay, which is the answer for the B part. Okay, which is the answer for the B part, which is equal to root 2r. The third thing they have asked is the magnitude of their relative velocity just before they collide. Okay, now just before they collide, the first particle was going inside the board, okay, and the second was going in the vertically downward direction with the same velocity, root gm by r. Okay, root gm by r. So now the relative velocity will be equal to, if I represent in this case, okay, the first one was going in this direction and the second one was going in the right hand side direction. Now both the velocities are perpendicular to each other. So the relative velocity over here will be equal to, since they are perpendicular, it will be equal to v1 square plus v2 square. Since v1 and v2 both are same, it will be equal to root 2 v1, which is equal to root 2 gm divided by r. This is the relative velocity of both the planets or both the satellites, okay, or whatever it may be, the particles, okay, just before the collision. So I have answered the question C also.